Right now we're looking at a phase angle that we, by calculations of the law of cosines, we determined that this voltage is about 120 degrees out of phase. And we noted that by noting the reference voltage between them, that 9.1415 on the bottom meter. And that's also, the other meter is reading 9.4, a little deviance. That's the totality of the voltages being measured in the circuit. We have another coil that's not yet been added. That is the 5.45 volts on the left hand side. And what we're going to do is we're going to go in there and add that voltage in series, and then go back and look at our original phase angle that we just observed to be near 120 degrees by those calculations there, using 5.7 volts and 9.2 volts as the hypotenuse. So we're going to go in there. Now we're going to sequentially add everything together. But first, before we do that, we want to show what kind of work the circuit's doing. The circuit's connected to a high voltage 42 to 1 step-up transformer. It's inputting 0.14 amps into the primary. Over here we have a 50 nanofarad cap being charged up to that higher voltage. This being charged to 57 milliamps. Everything about this situation is status quo. Nothing is wrong. We want to know as a ratio then what the most that we could obtain out using them two coils, if they were completely in phase, would be the addition of their voltages, which would be summarized as 4.9 plus 5.5 would be 10.4 volts in total opposition. Now we're going to go and add the third coil. We presently have 9.19 volts going into the transformer primary, 928 volts, 35. That is the third coil. We now have 13.25 volts sequenced from 4.8, 4.4, and 5.5, and we want to look at our total phase angles involved here now. On the two left, we have the 4.89, 85. We have this and this, with this measured in between. So we need to find out what that phase angle would be. And it looks pretty close to 180 degrees, but we'll have to figure that one out by simultaneous readings. And then we'll have to go over here and do the same thing for those three voltages all over again. And we note that now we have 0.20 amps inputted into the transformer and 82 milliamps on a 7,000 ohm reactance. That's about 80 times 7 for 560 volts. So we're going back to this problem. We got 4.4 squared plus 5.4 squared minus 8.7 squared, we'll call that 8.6 squared. We'll call that 8.7 since it's one wide fluctuation. And that divide by 2 times the sums, 8.4 times 5.4. It gives us minus 0.57. There's an inverse cosine of that. And that gives us that gives us 124 also. So apparently here that didn't change anything. But we know we've got something that's almost completely opposite in unity with that. And anything over 60 degrees found on that will be in excess to 180 degrees. And we can say then our capacitor is being charged by fields in an expanded time frame. You'll have to admit, the most we should be able to get will be the sum of any two voltages in time. And we have gotten better than that, which we've got 13.4 volts multiplied by 42 and displaying then 82 times 7 volts on the output. That output, once again, is convincingly over what would be available by ordinary means. Certainly so. And to conclude here too, we see that our inputs are 5.4, 5.2, and 4.9 volts from the stator, collectively being converted to 13.12 volts into the high voltage transformer. So we can see there that's an evidence for three opposites in time when we work with the checkers. When we play with these alterations, we're dealing with two opposites in time. But when adding this and getting over the sum of that, we must admit that that is acting as a third opposite in time. And this is then a time distortion device. Thank you.